Chapter 13, Magnetic Effect of Electric Current. In the previous chapter, we have already studied about the electricity. We learned about the heating effect of electric current, okay, in which we have studied heating effect of electric current. What could be the other effect of electric current? Okay, now the next, okay, which is the second effect for the electric current, okay, that we will study in this chapter. We know that an electric current carrying wire behave like a magnet. Okay, if the electric current carrying wire, okay, we have, okay, that will react as what, okay, or behave as what, okay, as a magnet, they will behave it, okay, as you can see in the figure 13.1. Let us perform the following activity to reinforce it. We see that the needle is diffracted. Okay, here in this you will see that needle, okay, which we have placed, okay, that will be what, okay, that will be diffracted. What does it mean? It means that the electric current through the copper wire has produced a magnetic effect. Okay, here you can see that electricity or electric current is flowing, okay, flowing, okay, as you can see that magnetic needle, okay, which will be diffracted from its original stage, due to which indicate that there is a certain magnetic effect on this, okay, on this we will see the magnetic effect. Thus we can say that electricity and magnetism are linked to each other. If we talk about that, then magnetism as well as electricity, okay, are interconnected with each other. Both of them are interconnected with each other. Then what about the reverse possibility of an electric effect of a moving magnet? In this chapter we will study magnetic field and such electromagnetic effect. Okay, in this chapter we will study that only magnetic field as well as magnetic effect, electromagnetic effect of a particular apparatus as well as structure or a circuit. We shall also study about the electromagnetic and electric motor, which involve the magnetic effect of electric current. Okay, in electric current, due to electric current you will see some magnetic effect, okay, and that phenomena which can be seen in electric motors as well as electric generator and in electric motor you will see such type of phenomena, electric current due to magnetic effect as well as many other things. And in electric generator you will see the electric effect of moving magnet, okay, moving magnet, electric effect of moving magnet as well as in magnetic effect of electric current, okay, both are reverse of each other. Okay, so in this chapter we will study that only. Now the magnetic field and field line, okay. We are familiar with the fact that a compass needle get diffracted when brought near the bar magnet. Okay, when we brought to the bar magnet, at that time compass needle get what? Okay, they get diffracted because of bar magnet. Because of bar magnet, we can see that compass needle get diffracted. A compass needle is in fact a small bar magnet. Okay, that is what? Okay, small bar magnet. The end of the compass needle point approximately towards the north and south direction. They are approximately okay, they are ended with the north and south direction. Okay, the end pointing towards the north are called north seeking or north pole. Okay, the point which are having north direction or north seeking, that is said to be north pole, as well as the end which point towards the south, that seeking a south seeking, that is said to be a south pole, okay, which we said as south pole and north pole respectively. Okay, once again I am repeating, if the end of that compass needle, okay, having a end point on north, okay, and pointing towards the north are said to be north pole, and end pointing towards the south are said to be a south pole. Through various activity we have observed that a pole ripple, while unlike pole what okay like pole ripples as well as unlike pole get what okay attracted each other. Unlike pole of a magnet attract each other. Okay, once again I am repeating, like pole, okay, like pole of a magnet, they get what okay they get repel, and unlike pole of a magnet they get what okay they get attract each other. Okay, as you can see that north is there as well as south is there. Okay, in magnet only you can see bar magnet only you can see that north n is written as well as s is written, okay, which indicate north side or a north pole, north seeking, and south side which is said to be a south seeking or south pole. Okay, and as you can see that iron filling near the bar magnet align themselves along the field line. Okay, the iron filling arrange themselves in the pattern as shown in the figure. Why do the iron filling arrange in such pattern? What does the pattern demonstrate? The magnet if exert its influence in the region surrounding it. Okay, as you can see that in a magnet surrounding that region, iron gets surrounded. Okay, and they get influence the region surrounding it. Therefore, the iron filling experience a force due to which you will see that iron which is there or iron filling they get a force, certain force, and due to which the arrangement will be seen as we have seen. The force thus exerted make it iron filling to arrange in a pattern. The force which is exerted by the magnet, okay, magnetic force which we say it as a magnetic force due to which what okay iron filling get arranged in the pattern as we have observed or seen just now. Okay, so this way due to the force magnetic force what will be seen, iron get arranged surrounded by the magnet. Okay, because of the magnetic force certain force is there, okay, which we say it is a magnetic force due to which iron filling get arranged, okay, surrounding the magnet. And the region surrounding a magnet in which the force of a magnet can be detected is said to be a magnetic force. Okay, so this region, okay, where a force of a magnet can be detected are said to be a magnetic field, which we say it as what okay magnetic field. Okay, the line along which the iron filling align themselves representing a magnetic field line, and line which is there along with okay iron filling align are said to be what okay magnetic field line, which we say it as a magnetic field line. Are there other ways of obtaining magnetic field line around a bar magnet? Yes, you can yourself draw the field line of a bar magnet. Okay, as you can see, okay, the field line around a bar magnet which we can see. Okay, which you can see field line around a bar magnet. This is said to be a field line. Magnetic field is the quantity that has both direction as well as magnitude. Okay, so magnetic field have both the quantity which two okay direction as well as magnitude. The direction of the magnetic field is taken to be the direction in which a north pole of a compass needle move inside it. Okay, direction is said taken what? Okay, direction of the magnetic field is taken to be the direction in which a north pole of a compass needle move inside it. Okay, that will be the direction of a magnetic field. Okay, therefore it is taken by the convention that a field line emerge from north pole and merge at a south pole. Okay, what the note the arrow marked on the field line in which figure 13.4. Okay, so there will be what okay convention that the field line emerge from north pole and merge at what okay south pole, okay, are taken. inside the magnet. Okay, the direction of the field line is from south to a north pole. Okay, inside the magnet you will see that what, okay, direction of a field line will be from where. Okay, inside the magnet we will see the direction of the field line is from south pole to its north pole. From south to pole it will be its field line. Thus the magnetic field line are close curved. Okay, which we have already seen in the figure. There will be what, okay, close curved. Okay, close curved will be there. And the relative strength of a magnetic field is shown in the degree of closeness of a field line. Okay, that will be seen. The field is stronger. Okay, the field, magnetic field which is there, that will be stronger. That is the force acting on the pole another magnet plays in the greater, where the field line are crowded. Okay, where what, okay, field line will be crowded. And the second what, okay, another magnet plays, okay, which have a greater. Okay, then what will be seen, the field line are crowded. Field line will be what, okay, crowded, because of placing a greater force magnet. No two field lines are found to cross each other. If they did, it would mean that at a point of interaction, the compass needle would point towards the two direction, which is not possible. Okay, which is not totally possible. If what, okay, two field lines are there, then what, okay, cross each other, they will cross each other. And if they did, okay, then what will be seen, that point of interaction. Okay, point of interaction will be what, okay, compass needle will point towards the two direction. Okay, and which cannot be possible. Why? Can a compass needle will give only one direction only. Okay, they will not give two direction. Okay, so it is impossible to compass needle for giving a two direction. Now the next is magnetic field due to the current carrying conductor. We have seen that an electric current through the metallic conductor produces magnetic field, which we have already seen. Okay, what, okay, electric current through the metallic conductor produce what, okay, magnetic field. During the passing of electric current in the metallic conductor, we will see a creation of magnetic field around it. And in order to find the direction of the field produced, let us repeat the activity. Okay, in which direction? As you can see, as you can see that here, we can see that okay. So if we see, okay, direction of a current is from this way. Okay, and here in this you will see the direction of a current is this way. Okay, so in both the cases you can see that, okay, here you can see that north and south is placed this way, south and north. But in this you will see that north and south will be from this way, north and south. Okay, which is totally reverse from each other. Okay, so from this you can see that if the electric current, okay, direction is different, then we will get different direction of a needle. Okay, a simple electric circuit in which a straight copper wire is placed parallel to and over a compass needle. The diffraction in the needle become opposite when the direction of the current is reversed. Okay, as you can see that when we are reversing a direction of a current, we will observe that what, okay, diffraction of the needle is also opposite. Okay. Okay, so it is totally depends on whom. Okay, direction of a current. If the direction of the current is opposite or reverse, then its diffraction of a needle is also opposite and reverse. Okay, So now the next is magnetic field due to the current through the straight conductor. Okay, now we will study that. What determines the pattern of a magnetic field generated a current through the conductor? Does the pattern depends on the shape of the conductor? We shall investigate this with an activity. We shall first consider the pattern of magnetic field around a straight conductor carrying current. Okay. First we will see that only. As you can see, okay, a pattern of a concentric circle indicating a field line of a magnetic field around a straight conducting wire. The arrow in the circle shows the direction of a field line. Okay, as you can see, okay, direction of the field line, which is circular. Same way, in the next you can see B, a close up of a pattern obtained. Okay, the pattern will be this way, circular form. Okay, orbit type. Okay, which we have studied as like a orbit. Okay, you can see it will be like a orbit type. Now, what happened to the diffraction of a compass needle placed at a given point? If the current in the copper wire is changed, to see this, vary the current in the wire. Okay, as you can see, the pattern will be changed. If the direction of a current is changed, then what will be seen? The pattern will also changes. We find that diffraction in the needle also changes. Okay, diffraction. Just now we have studied the current direction changes. From that, diffraction of a needle is also changes. In fact, if the current is increased, if we increase the current, okay, in the circuit, what will be seen? The diffraction also increases. So from this we can say that current is directly proportional with the diffraction. Okay, if the current increases, then diffraction is also increases, and if the current decreases, then diffraction is also decreases. Okay, so from this we can justify what? Okay, current, okay, direction of a current is directly proportional, and a proportion or an amount of a current is directly proportional with the diffraction. Okay, if we change a current direction, then diffraction is also changes. Same way, if we increase the amount of current, then diffraction amount also increases. Okay, it indicates that magnitude of a magnetic field produced at a given point increases as the current through the wire increases. Okay, just now we have discussed that if we increase the amount of current, then diffraction amount is also increases. Okay, what happened to the diffraction of a needle? If the compass is moved away from the copper wire, but the current through the wire remains the same. To see this, now place the compass at the farther point from the conducting wire. What change do you observe? We see that the diffraction in the needle increases. Okay, diffraction of the needle will what? Okay, decreases. Why? Because we are placing a compass far from a conducting wire. Okay, so as you can see that magnetic, okay, attracts a magnetic field or force will be decreased, but diffraction is also decreases with that. Thus, the magnetic field produced by a given current in the conductor decreases as the distance from it increases. Okay, so from this we can say that magnetic field produced by a given current, okay, in the conductor. In a conductor, what? Okay, given current is applied, okay, decreases as the distance from it increases. Okay, as the distance increases, okay, current in the conductor is also decreases. Okay, so as far, okay, the compass or a magnetic field, as much amount of current will be decreases. Okay, it can be noticed that a concentric circle representing the magnetic field around the current carrying straight wire become larger and larger as we move away from it. Okay, if we move away from it, then what will be there? It get larger and larger. Okay, huge, okay, big, okay, will be seen. So now the right hand thumb rule. Right hand thumb rule. A convenient way of finding the direction of a magnetic field associated with the current carrying conductor. Okay, as you can see in figure 13.7. Okay. Imagine that you are holding a current carrying straight conductor in your hand, in your right hand, such that a thumb pointed towards the direction. Okay, as you can see, thumb get pointed towards with okay direction of a current. Then your finger will whip around the conductor in the direction of the field line of a magnetic field, as shown in the figure. Okay, magnetic field which you can see. Okay, so this will be the what? Okay, this is known as a right hand thumb rule. Once again I am repeating, what is right hand thumb rule? Okay, if we perform a activity or experiment in which what we are doing, imagine that you are holding a current carrying straight conductor. Okay, current carrying straight conductor in your right hand. Okay, which we are taking in our right hand, and we are directing what? Okay, direction of a current. Our thumb is, and your finger grip, finger is grip. Okay, we have ripped our finger, and the direction of a field line of a magnetic field. Okay, that can be what? Okay, your finger will rip around the conductor in the direction of a field line of a magnetic field, as shown in figure, and this is called right hand thumb rule. Okay, magnetic field will be in this direction. Okay, and the current will be in this. Okay, so this way we can able to investigate a direction of a magnetic field during the passing of current. If we know the direction of a current, then we can able to find out a direction of magnetic field easily by which okay right hand thumb rule. Okay, right hand thumb rule are important for investigating a direction of a magnetic field. Okay, if we know a current direction, then we can easily find out a direction of magnetic field by right hand thumb rule. Okay, so it is important for finding out a magnetic field. Okay, if we know a direction of a current. Okay, now a new example. A current through a horizontal power line flow in the east to west direction. Okay, here you can see that the current is horizontally power line from where? Okay, east to west direction. What is the direction of a magnetic field? At a point directly below it and at a point directly above it. Okay, two conditions are there. The current is in the east to west direction. Okay, here you can see that current direction is from where? Okay, east to west direction. Okay, now applying the right hand thumb rule, we get that a magnetic field at any point below or above the wire turn clockwise in a plane perpendicular to the wire. Okay, when viewed from the east, and the anti-clockwise when viewed from the west. Okay, once again I am repeating what we are saying. If we are okay observing a current, okay, current is from where? Okay, east to west direction. Okay, now applying a right hand thumb rule, we are applying what? Okay, right hand thumb rule, in which we are getting that a magnetic field okay turns clockwise in the plane perpendicular to the wire. Okay, when viewed from the east. Okay, if we observe it from the east end, then a magnetic field will be from where? Okay, it will be from clockwise and anti-clockwise when viewed from the west end. Okay, so this will be the direction. Okay, from east we will see clockwise, and from west we will see anti-clockwise of a magnetic field. Okay, now the magnetic field due to the current through a circular loop. Okay, magnetic field line of a field produced by the current carrying circular loop. Okay, as you can see here. Okay, now here in this you can see that current is applied current is applied from here, plus and minus, you can see that. Okay, this is a plus and this is a minus. Okay, here we are applying a current. Okay, now we have so far observed the pattern of a magnetic field line produced around a current carrying straight wire. Suppose this straight wire is bent in the form of circular loop, okay, which you are seeing. Okay, and a current is passed through it. Okay, and also you can see that from the one end we are applying a plus, and from the second we are applying a minus. Okay, suppose this straight wire is bent in the form of a circular loop and a current is passed through it, and we are passing what? The current. How would the magnetic field line look like? We know that the magnetic field produced by the current carrying straight wire depends inversely of a distance from it. Okay, so similarly at every point of current carrying circular loop, the concentric circle representing the magnetic field around it will become larger and larger as we move away from the wire. Okay, if we move away from the wire, then you can see that it get what? Okay, larger and larger. Okay, by the time we reach at the center of the circular loop. Okay, when we reach a center of the circular loop, at that time what we are saying? The arc of this big circle will appear a straight line. Okay, straight line which you can observe it. Okay, every point on the wire carrying current will give a rise to a magnetic. Okay, every current which are passing, okay, they will give what? Okay, they will give a magnetic field. Okay, magnetic field, okay, appearing as you can see at the center of the loop. By applying the right hand thumb rule, if we apply right hand thumb rule, then what will be seen? It is easy to check that every section of a wire contributes the magnetic field line in the same direction with the loop, as you can see here. Okay, so this will be the what? Okay, field line as well as magnetic effect, and due to which you will observe. We know that the magnetic field produced by the current carrying wire at a given point depends directly on the current passing through it. Okay, so from this you can see that magnetic field which is produced is directly proportional to whom? Okay, current passing through it. Therefore, if there is a circular coil having n turn, how many turns? Okay, n turns are then what will be seen? The field produced is n times a larger as that produced by the single turn. Okay, it will be how much time larger? Okay, n time larger, and this is because of a current in each circular turn has the same direction, and the field due to the each turn has just add up. Okay, the direction will be same as you can see it. Okay, so here will be as you can see. Okay, so magnetic field produced by the current carrying circular coil. Now magnetic field due to the current in the solenoid. A coil of a many circular turns is insulated copper wire wrapped closely in the shape of a cylinder is called solenoid. The pattern of a magnetic field line around a current carrying solenoid is shown in figure 13.10. Okay, as you can see in figure 13.10. Okay, this will be our solenoid. Compare the pattern of a field with the magnetic field around a bar magnet, okay, which we have seen in 13.4. Do they look similar? Yes, they are similar. Both of them are similar. In fact, one end of a solenoid behave as a magnetic north pole. Okay, one end of a solenoid. Here you can see that will act as what? Okay, magnetic north pole, while the other behave as a south pole. The field line inside the solenoid are in the form of parallel straight line. Okay, as you can see, it will be what? Okay, parallel straight line is there. This indicates that the magnetic field is the same at all points inside the solenoid. So magnetic field is same around the solenoid or the solenoid. Okay, inside the solenoid. That is the field is uniform inside the solenoid, and which is uniform. Okay, as you can observe it. Okay. Okay, as you can see, a current carrying solenoid coil is used to magnetic ties steel rod inside it, electromagnetic, okay, which we said. A strong magnetic field produced inside a solenoid can be used as a magnetize a piece of a magnetic material. Okay, for magnetizing what a piece of magnetic material, this can be used like a soft iron when placed inside the coil. Okay, the magnet so formed is called electromagnet, and due to which you will see the magnet will be formed. Once again, I am repeating. A strong magnetic field produced inside a solenoid. A strong magnetic field is produced inside the solenoid. Okay, that is used as what? Okay, that is used to magnetize a piece of a magnetic material. Okay, to a piece of a magnetic material can be magnetized easily. Okay, by using this phenomena, like soft iron when placed inside the coil. Okay, when we are placing inside the coil, then what will be seen? A magnet so form. Okay, that will form a magnet because iron get magnetized, and due to which it will act as a magnet, and this type of magnet is said to be electromagnet.
The coil has length QR equals to L and width PQ equals to B. Magnetic field taken along x-axis is B bar equals to B I cap. Force acting on side PQ forming current element IB bar is F1 bar equals to IB bar cross B bar. Similarly, force acting on side RS forming current element minus IB bar is F1 dash bar equals to minus IB bar cross B bar. The forces F1 bar and F1 dash bar are equal in magnitude, opposite in direction, and collinear. Hence, they cancel each other. Now, force acting on side QR forming current element minus IL J cap is F2 bar equals to minus IL J cap cross BI cap equals to ILB K cap. Similarly, force acting on side SP forming current element IL J cap is F2 dash bar equals to IL J cap cross B I cap equals to minus IL B K cap. The forces F2 bar and F2 dash bar are equal in magnitude, opposite in direction, but non-collinear. So they give rise to a torque couple. Figure shows the top view of the coil. Here, A bar is the area vector of the coil, which makes an angle theta with the magnetic intensity. B bar along x-axis. By definition, magnitude of torque couple equals to magnitude of a force